Good morning.
Good morning, madam.
Good morning, Dilshan. Where are the others? 30 students are there. You don't even want to switch on your mics to say good morning.
Good morning, madam.
Good morning, Nadeem. Yeah, once in a while, it's good to switch on your mics and like unmute your mics and say something, right? So otherwise, in a class, we usually see you and we can talk with each other. But here also, at least up to some point, without just using always the chat window, you can say something, right? Okay, so yeah, it's 9:32 and 31 students are here. Yeah, the thing is like everybody log on sharp at like 9:30 to 9:35. It should be the other way around, at least 9:25 to 9:30, because I like to start at 9:30 sharp time. But every time I check, it's about like 10 to 20 students. So that's why I wait about 2 minutes. Okay, so get used to it. Be punctual. That's a good quality that you can develop, right? Okay, so first of all, the homework. Yeah, I gave you homework last time and there were 51 submissions today morning. Last night when I checked, there were like 41. I checked those answers. Yeah, almost all of you have done it correctly. So you had this matrix A, part 2112 or something. And if you calculate the, did I switch on the recording? Yes, okay, fine. Yeah, lambda 1 and lambda equals 3. And when lambda equals 1, the eigenvector equals 1 minus 1. And here it's 1, 1. And once you normalize it, you get here 1 over root 2 minus 1 over root 2. And here 1 over root 2, 1 over root 2. Those are the normalized eigenvectors. And then you had to use the spectral decomposition and reproduce your matrix A. So yeah, you all have done it. I'm just trying to say some drawbacks, like those are not really drawbacks for a homework, because for homework you have time, you can do anything, right? But when a question is given for an exam, always answer the question, right? Don't try to write a lot of unnecessary stuff. Those are correct, but I mean, some of you after finding E1 and E2, you have showed those are really normalized using E1 prime E1, showing this equals 1. It must be, right? Because you come from here to here using that condition. X1 prime x1 equals 1. So when you have to find the normalized vectors, once you use this one and calculated that one, then that's the answer, right? That's a normalized vector. So you don't have to show again that it's equal 1 and even those are orthogonal like E1 prime E2 equals 0. You don't have to show them. Some of you have showed. That's fine because it's the homework. But for an exam, I'm just saying this when I usually noticed when I grade the exams for students. Some students write pages of unnecessary stuff, correct stuff, but some proofs and all which are not asked you to do. So then sometimes the required answer is not there. Maybe they ran out of time or something. So when you do an exam, please remember you have to answer the questions that were asked, right? So don't try to write a lot of other stuff as well. briefly give the answer because we just look for the answer, right? So just keep it in mind here. There's no issue at all for the homework. It's good that you have showed this also. That's good. But I'm just saying when you write the answers for an exam, right? During an exam, because the time is limited. So the time is given to answer those particular questions. So the answers for those particular questions must be there. Otherwise, you wouldn't get marks, even though there are a lot of other stuff, right? So that's why I'm just saying this. Okay. Other than that, yeah, rest of it, it's okay. Like all of you have showed, like A equals that one, like lambda 1, E1 transpose plus lambda 2, E2 transpose. So calculating this, you have showed, that's it, right? Okay, so that's about the homework. Anybody having any questions about the homework? And 2 students haven't submitted. I'm not going to read their names here, but when I ask you to do a homework, it's good for you to do it, right? So please do. Okay, so again, I'm asking any questions?
Excuse me, madam.
Yes.
This is a very basic question regarding last week's lecture.
Yes.
When we were proving the variances of random samples, there are now x1, x2, and all are individual observations, right?
Yes.
So now we took the variance of say x1 as sigma squared.
You are asking univariate or?
Last week for a random sample, madam, you said that x1, x2, like if you take a random
that's a
sample.
multivariate case. Then not sigma square, you are saying sigma, right?
Yeah, I'm asking madam how we that was for a, so madam, if you that's a 1 cross p vector, right? That's an individual observation, right?
These are individual observations, x1, x2 up to xp, xn, sorry. But all of them are p by 1 vectors.
All right. Okay. Okay, madam. No
Right?
problem. Then okay. Thank
Okay.
you.
So yeah. Maybe others also having the same question. Thanks for the question, Dilshan. And like if you have like this, an observation is this, right? So x1, 1, 1, 2 up to x1 p, 2, 1, 2, 2 up to x2 p. So this is your first observation. This is actually that x1 transpose. Right? That's the first observation. This is your second observation, x2 transpose. Right? This is your nth observation, whatever this one, xn transpose. So yes, when we look at the data matrix, we see it as a 1 by p vector, but we usually say each observation is a p by 1 vector, right? Same as mu and x bar, right? So these are individual observations, and observation is a p by 1 vector, right? I hope it's clear for everybody. Please ask if you have any more questions. Yeah, it's good. Like this is the start of the lesson. I mean, the subject. So the things should be clear to go forward.
So, madam, the p values that are there, it's for the p parameters, right?
Yes, P parameters means P responses.
Okay. So, madam, like now that's like age, weight, and those for the independent variables. So, how can we define the variance for an individual observation, madam?
Yeah, the thing is these are not independent. Dilshan, those are correlated, right? Yeah. So for each observation, like that's why I actually tried to go with the univariate case. In univariate also we say x1, x2 up to xn. These are just scalars, right? 1 by 1. If that's a random sample from normal mu sigma square, that means for each observation, we say the variance is sigma square.
Yes, madam. Like, but
you are asking how do we say that, right?
Yeah, like how individual observations we can define a variance for individual observations, madam.
Yeah, we usually, that's, and when we say an observation, it's a random variable, right? A random variable always have a distribution, right? How do we define X bar as a distribution? In the same univariate, I mean, we say this one is sigma square over n, right?
Yeah.
So how do we define that one?
Or by taking the summation of the individual observations and dividing by n squared.
Yeah, that's true. But I mean, how, like for a sample, X bar is also a single value, right? I'm asking, how do we define a variance for a single value there?
Yeah, madam, I never quite understood that.
Okay, yeah, the thing is like, okay, I'll explain like this. This is the way, right? When you have a population, so you have your x's here, we say normal mu sigma square. These are univariate, right? So you take a sample of size n and you calculate X bar, right? That is the X bar we have here. But X bar is not a single value. It's a variable. Only, remember, only a random variable has a distribution always, right? So X bar is also a random variable because you can take different samples, right?
Yes, madam. Okay, I
Of
got
same
it.
size. Yes, so it's going to be like, we'll say K samples. So you have different mean values there, right? So that's why X bar becomes a random sample. Sorry, random variable, right? X bar is a random variable. So we define a distribution for X bar because X bar is a random variable. Same way, X's are also random variables. So it can be any value that we take from here, right? So when we define a population distribution, any random variable in that one has that distribution, right? For any X. Because this is not X1 has that distribution doesn't mean X1 is just a single value, right? Because it's also a random variable, right? That's why it has a mean value and a variance value, right?
Okay,
Those
madam,
all
thank
these are
you.
random variables. Is that clear?
Yes, madam, now it's clear. Thank you.
Okay, okay. Anything else? Always remember this part, Darune, always a random variable has a distribution, right? Not single value. So yeah, that's why we never write like mu has this distribution or anything. Mu is a single value because for the population, mean every time it's just a single value. It can never be a random variable, right? It's a single scalar value. But when we say an observation, it's going to be a random variable. When we even say X bar, the mean of a sample, that's also a random variable because that differs for different samples, right? Likewise, each observation is a random variable and also mean is a random variable, right? Any other questions? That's good. I always like when there are questions. Sometimes I may not be able to answer even because you may think ahead of me, but that's fine. I can find out and give you an answer. So it's always good to ask questions because now you are in third year, you are statistics honor students. So statistics honor students means you cannot just go through the surface, right? You have to think to the deep into the subject because you have to have a good knowledge in statistics. So even though you haven't thought about these things previously, at least now start thinking about this stuff, right? That's why I always say the basics. Basics are really important to go forward. If you go for like higher studies and all, like it would be really good that if you know the basics properly. Okay, so anything more? Any questions? Okay, then come back to the lesson. Yeah, first one. Yeah, last time we considered these numerical summaries of data, multivariate data. Remember, we just considered sample mean, vector. Yeah, I have to make some corrections in these places, not really corrections, but sometimes I miss this underline. To say it's a vector, right? X bar is an unbiased estimate of mu and its covariance matrix is sigma over n. So that's about X bar, and remember S is the sample variance covariance matrix, right? So first property we already proved, and we are in the second property, right? And here, like we just defined the mean and variance of X bar, right? The distribution of X bar, but the proper distribution we haven't defined because we haven't talked about the distributions of multivariate data yet, right? But when you have your univariate cases, so when Excel has a distribution, so if it's normal distribution, we say definitely X bar. What is the distribution of X bar in this case? If X's are normal, you know these things, I'm pretty sure.
Mean mu and variance sigma squared over n.
What's the distribution?
Normal.
That's also normal. Okay. Who was that? Does it? I don't know. I didn't see who that was. Anyway, yes, it's normal with mu and sigma square over n, right? The normality is defined there. And if you don't know the original distribution with mu and sigma square, then we have a theorem to get the distribution of X bar. What is the theorem?
Central limit theorem.
Yes, central limit theorem. Yes, Shashika. And yes, Rukshala. You answered in chat. Yeah, it's a central limit theorem. So what does it say? The central limit theorem. No matter what the original distribution is, we say X bar has what? We don't know the original distribution, but still, according to the central limit theorem, X bar has a answer. Normal distribution. Yes, Situmi. Yes, Tasneem. The others. Yes, it's normal with same parameters, mu and sigma square over n. What's the condition?
For large samples.
Yes, that's it. When n is large, right? N tends to infinity. We say X bar has a normal distribution with mean mu and variance sigma square over n, right? Central limit theorem, remember that. You will prove that, and even, I don't know whether you had the R class. In simulations, you have like, with simulations, we also show this. Like even if you take, yeah, the question earlier I asked related to Dilshan's question, like the distribution of X bar, we can take a bigger population and we take different samples. And like not a small number, like if you take like 1, 2, up to 10, 100 or something, you can draw a histogram for the distribution of X bar. And you can see no matter what the original distribution is, your X bar has a normal distribution. We usually do it with like exponential different distributions. So you know exponential is a skewed distribution, right? But gamma, anything. But you can see X bar has a normal distribution, right? That's the central limit theorem. So n is large. Yes, I said 100 here, but you know that we even say n greater than 30, then the central limit theorem is valid, right? Yeah. Nimni and Ashoka, you answered in the chat. Okay, fine. Yeah. So this is actually related to the central limit theorem in univariate case. But as we haven't talked about the distributions of multivariate data, here we just considered mean and variance only, right? The distribution part we haven't talked yet. Okay, yeah. Coming back to the second property, last time we started this, the sample covariance matrix is symmetric and positive semi-definite, right? We usually work with positive definite ones, but according to the theory, it's a positive semi-definite matrix. So recall S, we can write S in this form. We showed that earlier. So now to show this is symmetric and positive definite. Sorry. Symmetric and positive definite. So S equals 1 over n minus 1 x transpose hx, where h equals I minus 1 over n 1 transpose, right? So we already showed that H is symmetric. H symmetric means H transpose equals H. So in that case, S is also symmetric, right? Because S transpose becomes S if H is symmetric. So we proved that part, and then to continue with the rest of the proof, I said we have to have H to be idempotent. So I ask you to prove this if you can. Anybody did it? You can do it now. You just have to multiply the terms, right? I times I minus 1 over n 1 transpose. Again, I times that, another one. Then the last two terms, multiplication, you have 1 over n square, 1 transpose, 1 transpose. Okay, so it's I minus 2 over n 1 transpose. What's this term? You can see this becomes H if this one is, the last term is again 1 over n 1 transpose, right? Because you have minus 2 over n here. So if you have plus 1 over n, then that equals H. Is that true? 1 over n square. Can you simplify this? I'm asking what's 1 transpose 1? That multiplication. Remember 1 here was n by 1 unit vector. No, Hashini. 1 transpose 1. Yes, Nadeem, correct. Yes, Tarushi. Yes, Vibhanga. Yes, Ishan. Others? Yes, Ashoka. Yes, Pavanti. Yes, Pavan. Yes, Sevandi. Yes, Tasneem, Nimasha, Kalpani, Hashan. Yes, right, it's n. 1, 1 transpose equals n. Is it clear? Like 1 is n by 1 unit vector. So when you try 1 transpose 1, that's like 1, 1 up to once, again 1, 1 up to once, right? If you multiply, so this is 1 by n by 1. So in terms, just get mini, right? Yes, so that equals n, right? So you have 1 n 1 transpose. 1 n cancel off, it's simply 1 over n 1 1 transpose. So it's I minus 1 over n 1 1 transpose, which is h. So h is idempotent. Is that clear? Any question here? No questions? So, okay, then we'll continue with the proof. You can write this down. I have written that proof is an exercise. I didn't expect you to prove this by your own, right? Some places I have written proof exercise because I didn't want to type it actually. So we are going to write it down here, but once I did it in class, then you should be able to do it later, right? So here, let A be any non-null P by 1 vector. So remember, we have to prove that S is positive semi-definite. So if you remember the property for positive semi-definite, remember A is positive semi-definite if for any non-null vector x prime ax greater than or equals 0 and equality occurs for at least one x, right? At least one non-null x. So there's at least one non-null x. The equality occurs. Right, so that's the property positive semi-definite. So we take a vector A, a p by 1 vector, non-null 1, right? So we have to show this eighth prime is A. So that's how we show for non-null A. To show that S is positive semi-definite, we have to show that this part is greater than or equals 0, right? So simply plugging in 1 over n minus 1, A transpose, X transpose, H, X. Sorry. X is the data matrix. It's not a vector. You can check the dimensions and see whether I have written something correct. So what's the dimension A transpose? A is P by 1. So A transpose 1 by P. X transpose. What's the dimension X transpose? Yes, Ashoka, correct. Nadeem, This is not the vector X. This is the data matrix, right? So what's the dimension of X transpose? Yes, Samadhi. Yes, Vibhanga. Vibhanga or Vibhanga? I don't know. Yes, Oshada. Yes, Dasita. At least for one time, we had to switch on the videos and see everybody, right? Maybe at the end of the class, we'll see. Other X transpose. What's the dimension? Yes, Yashika. You know that S is P by P, right? 1 over N minus 1, X transpose HX. It's P by P. So X is our usual data matrix, which is N by P. So X transpose is P by N. Yes, Pawan. It's P by N. If you check, H is actually N by N. And X is again N by P. So A is again P by 1. So you can see all the dimensions, whether those are correct. P, P, all are confirmable, right? Are confirmable, that's the word. I forgot last time, I guess. Okay, so finally, you have X prime AX to be a scalar, A prime is A to be a scalar, right? Okay, so those are the dimensions. So we have written something correct. Now, here comes what we just showed. We just showed that H is symmetric and idempotent, right? So we can write this one as A transpose, X transpose, H we can replace by H times H because it is idempotent. And one H, the first H, I am going to replace with H transpose because it's symmetric, right? Since H is symmetric and H is idempotent. That's the reason that we can write it like this. Okay, so you can write this one as now 1 over N minus 1 H X A transpose, right? Times H X A. Okay, now tell me the dimension of HXA. Yes, Pavanti. Yes, Shashika. Yes, Ashoka. Himasha. Situmi. Oh, Situmi. Oh, other way. I'm asking HXA, not HXA transpose. Probably you answered for HXA transpose. Yes, Navoda. Yes, Dilshan. Yes, Kalpani. Yes, Ketmini, Nirasha. Oh, Devni. power 1, yes, right? It's n by 1. So h plus hxa is n by 1, and this one transpose 1 by n. I don't like this because otherwise we'll mix it, right? So we can write it as, so it's a vector, right? It's an n by 1 vector. So we can write it as 1 over n minus 1, something like y transpose y, where y equals h x a n by 1 vector. If y is an n by 1 vector, what would be y transpose y? Suppose y is simply it's an n by 1 vector, right? Just 10 elements there. Then what's y transpose y? Yes, it's a scalar, but yeah, both Nadim and who is this? Nimni. Yes, it's a scalar. So I'm asking what's the scalar value? Yeah, it's 1 by 1. That's correct. Dimension is 1 by 1. Yes, Shashika, correct. Y transpose y equals only one answer. Sum of yi square, right? Sum of yi square 7. Okay, I goes from 1 to n. Right. So it is sum of yi square. So sum of the squares, we know, always positive, right? Positive or 0 if y is all the y values equal 0, right? So we can say this one is, yeah. Further we can write 1 over n minus 1 summation yi square. So definitely this one is greater than or equal 0, right? 0 occurs if all the elements in y equals 0, right? So even though our A is non-null, there is a chance that all the y's equal 0 because that's hxa, right? According to the elements, we may have all the yi's equal 0. Okay, so we just proved what we needed, right? That's positive for, and there can be a situation where the equality occurs, that is when all the yi's equal 0 or y equals a 0 vector, right? Okay, please write this down. I'm going to the next page. I hope you are done writing. If you have not, you can say me now. Okay, since A is arbitrary, A transpose A greater than or equal 0 for all non-null A. This implies that S is positive semi-definite. n minus 1 is a constant, right? We have 1 over n minus 1 part, but still it's a constant. So that's the proof that S is positive semi-definite. But as I said, we usually work with positive definite matrices because in most of these hypothesis testing and all, we have to work with the inverse of the matrices. Remember, if we have a positive semi-definite, that means if equality occurs, then it's singular, right? In that case, there's no inverse, but we have to work with inverses. So mostly with the data, we have positive definite matrices. Right? Any question? That is the summarization part of multivariate data. So we learned some graphical techniques and also numerical summaries with X bar and S. Right.